Right now, a machine older than most of your parents is running on less electricity than a refrigerator light bulb, sitting so far from Earth that a single word sent to it takes almost a full day just to arrive. And it is still, right now, listening to something no human being has ever heard before. This is the real story of Voyager 1, and where it stands in 2026 is stranger than anything its own engineers expected back in 1977. When Voyager 1 launched in September of 1977 alongside its twin Voyager 2, the plan was modest, almost small by today's standards. Fly to Jupiter, fly to Saturn, take a close look, send back pictures, and then fade quietly into history after about 5 years. Nobody involved in the design expected these two machines to still be transmitting data half a century later, let alone to have left the solar system entirely. The only reason such an ambitious path was even possible in the first place came down to a rare planetary alignment that occurs roughly once every 175 years, one that placed Jupiter, Saturn, Uranus, and Neptune all on the same side of the Sun at the same time. That alignment let engineers design a route where each planet's gravity could fling the spacecraft forward to the next one, a trajectory NASA nicknamed the Grand Tour. The launch order itself hinted that something unusual was already unfolding. Voyager 2 actually lifted off first, but 16 days later, Voyager 1 launched on a faster path and quickly passed its twin. Just 13 days after launch, from more than 11 million kilometers away, Voyager 1 turned its camera around and captured something nobody had ever seen before. Earth and the Moon together in a single frame from deep space, our planet reduced to a tiny blue point suspended in total darkness. Even at that early stage, the mission was already turning ordinary technical milestones into moments that forced people to look at their own world differently. By early 1979, as Voyager 1 approached Jupiter, it found a planet unlike anything anyone had imagined from ground-based telescopes, a giant world wrapped in violent storms, brutal. Radiation belts and a system of moons complex enough to resemble a miniature solar system on its own. The flybys of Jupiter and later Saturn delivered a wave of discoveries that reshaped planetary science almost overnight, revealing thin rings nobody knew existed, moons nobody had catalogued, and environments no telescope on Earth could have predicted. The most consequential decision of the entire mission came at Saturn, where engineers chose to fly Voyager 1 close past Titan, Saturn's largest moon, to study its thick, mysterious atmosphere. That decision came with a permanent cost. Saturn's gravity bent Voyager 1's path sharply out of the flat plane where all the planets orbit, which meant it could never visit another planet again. From that moment forward, Voyager 1 and Turk 1 stopped being a planetary explorer and became something else entirely, a boundary breaker, accelerating into the fastest spacecraft humanity had ever built and heading on a one-way path toward the outer edge of the Sun's territory. Before any of that outer system drama unfolded, though, engineers back on Earth made a decision that had nothing to do with physics at all. Attached to the side of each Voyager spacecraft is a golden phonograph record, roughly the size of a dinner plate, containing a carefully chosen snapshot of life on Earth. Greetings. Recorded in 55 different languages, natural, sounds like thunder, wind, and whale song, more than 100 images encoded as data showing landscapes, animals, and everyday human life, and 90 minutes of music spanning cultures and centuries. The idea, championed by a small team that included astronomer Carl Sagan, was almost absurdly optimistic for a mission originally scheduled to last just 5 years. But this record might one day drift close enough to another civilization to be found and understood, and that even if it never was, sending it represented something worth doing on its own terms. Every version of Voyager 1's story, from its first photograph of Earth and the Moon together to its final science instrument, Someday Going Dark, has that same disk riding along with it the entire way. An artifact nobody expected to still matter 50 years later, quietly outlasting almost every other part of the mission's original plan. The Jupiter flyby alone dismantled decades of assumptions in a matter of days. What had looked from Earth like a plain, distant gas giant turned out to be a violent, constantly shifting world surrounded by moons, behaving almost like their own solar system. Voyager 1 sent back images of faint rings nobody had detected before, along with several newly discovered small moons. Jupiter's great red spot, long visible through backyard telescopes as a reddish smudge, was finally seen up close and confirmed to be a storm and larger than Earth itself, rotating counterclockwise. A centuries-old atmospheric monster still raging on the planet's surface. But the real shock came from a smaller world entirely. Io, Voyager, detected active volcanoes erupting on its surface, the first time humanity had ever observed active volcanism anywhere beyond Earth. Io wasn't a dead frozen rock. It was violently alive, and it remains the most geologically active place known in the entire solar system. Then there was Europa, its cracked, icy surface hinting at something even stranger underneath. Voyager's images suggested a vast ocean of liquid water hidden beneath kilometers of ice, quietly introducing an idea that still drives planetary science today, that one of the best places to search for life might not be a planet at all, but a frozen moon circling a much bigger world. After Jupiter, Voyager 1 used gravity itself like a slingshot, accelerating towards Saturn and arriving in 1980, carrying more momentum than any spacecraft before it. Saturn, long imagined as elegant and simple, with its turned out to be far more complicated than anyone expected. What looked from Earth like one thin ring exploded on closer inspection into hundreds, even thousands of narrow-layered ring structures, constantly shifting rather than fixed in place. Voyager 1 also found several new moons, including Mimas, whose massive crater made it look eerily like a small moon-sized battle station drifting through space. But the most important encounter by far was with Titan. Voyager 1 couldn't actually see Titan's surface because its thick atmosphere was nearly opaque to visible light. Still, by analyzing what that atmosphere was made of, scientists uncovered something remarkable. Titan is so cold that methane behaves there the way water behaves. On Earth, existing as a solid, a liquid, and a gas. That single discovery opened the door to the idea of lakes and rivers on a world far from the sun, an idea that reshaped how scientists think about chemistry and habitability across the entire solar system. The close pass by Titan came at a price, since Saturn's gravity permanently redirected Voyager 1 out of the solar system's plane, ending its career as a planet visitor for good. In exchange, it left behind discoveries so significant that the solar system itself no longer felt familiar to the scientists studying it. After years of quiet travel through empty-seeming space, Voyager 1 finally reached a region no human-made object had ever touched. On August 25, 2012, its instruments picked up something extraordinary, a sudden drop in charged particles streaming from the sun, paired at the same moment with a sharp spike in high-energy particles arriving from deep in the galaxy. This wasn't a slow fade. It was an abrupt shift, almost as if the spacecraft had physically struck an invisible wall. Voyager 1 had crossed the heliopause, the boundary where the solar wind finally runs out of strength and true interstellar space begins. Scientists had long assumed this region would behave like a gentle, gradual gradient, solar influence slowly thinning out over a wide stretch of space. The data told a completely different story. The sun's protective bubble, called the heliosphere, ended sharply, forming a real measurable membrane where plasma from the sun collided directly with plasma from the space between stars. In that instant, Voyager 1 stopped being a spacecraft, shaped by our star's environment, and became something governed instead by the galaxy itself, the first time in history a human-made object had physically pushed past the sun's reach. Crossing that boundary didn't just redefine where Voyager 1 was, it revealed that interstellar space is not empty and not silent. For more than 24 billion kilometers away, Voyager 1 recorded a steady cosmic hum sitting at around 3 kilohertz, a signal that lasted for nearly 3 years. Scientists described it as a thin metallic tone, almost as if the space between stars were quietly resonating in the background. That signal turned out to be interstellar plasma waves, and by studying it, scientists could actually measure the density of the material drifting between stars, effectively turning sound into a tool for mapping something completely invisible. At the same time, Voyager's readings showed that the interstellar magnetic field out there was far stronger than anyone had modeled, 2 to 3 times more intense than expected, pressing against the heliosphere with nearly 10 times more force than predicted. That finding means our entire solar system sits inside a tightly compressed bubble, constantly pushed and reshaped by the surrounding galaxy, rather than floating freely in open space. Voyager 1's data also helped confirm that the sun sits inside something called the local bubble, a cavity roughly 1,000 light-years across, carved out by ancient supernova explosions long before humans existed. That bubble shields our solar system from a lot of interstellar dust and changes how cosmic radiation reaches Earth, meaning that without most of us ever realizing it, life here has been sitting inside a kind of a natural cosmic shelter this whole time. It's worth pausing on just how strange this makes the boundary itself. Before Voyager 1 actually crossed it, most models treated the heliopause as a soft, blurry edge, something a spacecraft would drift through gradually over months, without any single dramatic moment marking the transition. Instead, the readings on August 25, 2012, showed something closer to a sharp membrane, charged particle counts from the sun collapsing within a matter of hours rather than fading slowly across weeks. Scientists studying the handoff realized they were looking at something closer to a genuine physical wall than a fuzzy zone, a place where 2 different kinds of plasma, one shaped by our star and one shaped by the wider galaxy, meet invisibly resist mixing into each other. That sharpness became one of the most cited surprises in the entire mission's later career, reshaping textbook diagrams of the solar system almost overnight, and forcing physicists to rebuild their models of how stars interact with the space around them. Voyager 2 followed its twin across that same boundary 6 years later, in November of 2018, arriving at a different point along the heliopause and giving scientists a second independent measurement of the same structure from another angle entirely. Comparing the two crossings let researchers confirm that the heliopause isn't a perfectly smooth sphere surrounding the Sun, but something closer to an irregular dented shape, pushed and pulled unevenly by the pressure of the interstellar wind blowing against it from one general direction, as the Sun, Clear's throat, moves through the galaxy. Having two independent data points gathered years apart and from different locations turned a single strange measurement into an actual confirmed feature of our solar system's outer shape, something no telescope on Earth could ever have detected on its own. Now, here's where the story catches all the way up to today. Because what's happening to Voyager 1 in 2026 is its own kind of quiet drama. The spacecraft is currently sitting somewhere around 25.5 billion kilometers from Earth, about 170 times the distance between Earth and the Sun, still moving outward at roughly 17 kilometers every second. A radio signal now takes close to 23 hours to travel one way between Voyager Sun. We're one in mission control, which means a single round-trip command and confirmation eats up nearly 2 full days. On November 18th, 2026, at a precisely calculated moment, Voyager 1 is expected to cross a genuinely historic threshold, becoming the first human-made object to sit a full light day away from Earth, a distance so vast that light itself, the fastest thing in the universe, needs an entire 24 hours to cross it. But getting there is costing the spacecraft almost everything it has left. Both Voyager probes run on radioisotope thermoelectric generators, devices that turn the heat from slowly decaying plutonium into usable electricity. That power source has been fading by about 4 watts every single year since launch, a slow, steady drain that never stops and can't be reversed. To stretch the mission as long as possible, engineers have had to shut down instruments one by one in a carefully chosen order, sacrificing pieces of the spacecraft's senses to keep its heart beating. Voyager 1's cameras went dark back in 1990, right after they captured the mission's famous final portrait of the solar system. Its plasma science instruments stopped working reliably by 2007. Its ultraviolet spectrometer, useful for longer than most expected, was finally switched off in 2016. The cuts have only gotten more serious recently. NASA turned off Voyager 1's cosmic ray subsystem in February of 2025 to conserve power, and then, in early 2026, turned off its low-energy charged particle instrument as well. According to NASA's mission team, that leaves only 2 working science instruments still active on Voyager 1 as of this year. The magnetometer, which measures the magnetic field around the spacecraft, and the plasma wave subsystem, the very instrument responsible for picking up that eerie interstellar hum. Kareem Badruddin, the Voyager mission manager at NASA's Jet Propulsion Laboratory, has been blunt about what these decisions actually mean, saying that shutting down a working science instrument is never anyone's first choice, but that it remains the best option available to keep the spacecraft alive. Engineers aren't simply letting the mission fade quietly, though. NASA's team has been developing an ambitious software fix, nicknamed internally as the Big Bang, aimed at squeezing more efficient operation out of the aging spacecraft and potentially even allowing some previously shut down instruments to be brought back online for short stretches. It's an unusual kind of optimism for a machine pushing 50 years old, running on hardware, weaker than the processor inside a basic calculator, and drifting through an environment where temperatures sit close to absolute zero, and cosmic radiation constantly threatens to damage what little circuitry remains functional. The logic behind that kind of software gamble comes down to a simple trade-off engineers face every single year now. Every watt of power still available on Voyager 1 has to be rationed between keeping its heaters running, so delicate components don't freeze and crack in the cold of interstellar space, and keeping its remaining instruments powered up long enough to keep sending back readings. Shut off too many heaters too soon, and critical hardware could fail outright. Keep every instrument running too long, the spacecraft could simply run out of power years earlier than necessary. NASA's own internal estimates from 2025 suggested that without any further conservation moves, Voyager 1 might have had only a handful of months of usable power left before mission controllers would have had to declare an end to operations altogether. With careful watt-by-watt rationing instead, the team now believes at least one science instrument could realistically keep functioning into the 2030s, stretching the mission nearly 6 decades past its original 5-year plan, though officials are careful to note that any unexpected hardware failure could still cut that timeline shorter without warning. None of this is guaranteed to work forever, and mission leaders have been honest about that. Suzanne Dodd, the Voyager project manager, has explained that if the propellant lines on either spacecraft freeze, causing their antennas to drift away from pointing at Earth, the mission would essentially end immediately, since there would be no way to send a signal back to receiver. That isn't listening in the right direction anymore. The team's current hope is to keep the magnetometer and plasma wave subsystem running on both spacecraft, along with the cosmic ray subsystem on Voyager 2, letting the probes function almost like weather stations scattered through interstellar space, quietly sensing the environment around them long after their cameras and other instruments have gone silent for good. This fragile, patched-together survival isn't new either. The spacecraft have already faced moments that nearly ended everything. On November 14th, 2023, Voyager 1 suddenly stopped sending back anything meaningful, transmitting nothing but streams of garbled binary noise, a signal that suggested something deep inside its systems had broken. Engineers eventually traced the problem to a failure inside the flight data system, one of the most critical parts of the entire spacecraft. Rather than accept the loss, the team attempted something extraordinarily risky, rewriting and relocating decades-old code into whatever healthy memory remained, a procedure demanding surgical precision and a lot of patience, given that every single command took nearly a full day to arrive and another full day for confirmation to return. The tense process began on April 18th, 2024, followed by days of total silence that stretched nerves to the limit. Then, on April 20th, Voyager 1 spoke again. Engineers described the moment as watching the heartbeat of an aging space traveler start up once more. Voyager 2 had its own brush with disaster months earlier when a routine command accidentally tilted its antenna just 2 degrees away from Earth, a tiny misalignment that nearly severed contact permanently until a powerful signal sent from a tracking station in Australia managed to restore the connection after 37 agonizing hours of silence. Moments like these reveal something important about what these two machines actually are. They were never just hardware. They're aging explorers, fragile and stubborn in equal measure, still pressing forward, even as their voices grow fainter. Every year, proof that long after their own designers expected them to fail completely, they're still out there, still answering, still carrying a piece of human curiosity into the dark. Voyager 1 never collided with a physical object out in deep space. But what it ran into may be even more significant than any solid obstacle could have been. It reached a boundary that can't be seen, crossed a frontier with no wall or marker announcing its edge, and entered a region where the underlying rules of space quietly change. Beyond the heliopause, Voyager 1 discovered that interstellar space isn't empty, isn't silent, and isn't passive. It found pressure where scientists expected open freedom, structure where they imagined total emptiness, and a steady cosmic hum where they assumed nothing but absolute silence. It revealed that our entire solar system lives inside a fragile bubble, compressed and shaped by forces far older and far stronger than our own sun, that even the space stretching between stars has real texture, density, and sound. All of that was uncovered by a machine that was never built to survive this long, running on a power source weaker than a household appliance, guided by computers less capable than a basic modern calculator, and somehow still expanding what humanity understands about where we actually are. As Voyager 1 continues drifting toward the far edge of the solar system's outer shell, a journey that will take centuries just to begin reaching the Oort cloud and tens of thousands of years to fully cross it. It's carrying something with it that matters, more than any single instrument reading or data point. It carries a record of us, our voices, our music, our images, and a quiet declaration that we existed, that we wondered about what was out there, and that we dared to reach beyond the limits of our own small world. Whether anyone or anything ever finds that message is almost beside the point. What matters is that we sent it anyway, long after Voyager 1's last instrument finally goes dark and its last signal fades into silence for good. Sometime probably in the 2030s, if current power projections hold, the spacecraft itself will keep moving forward regardless. A small fragment of humanity, traveling through the dark on our behalf, carrying nothing but momentum and memory into a future none of us will ever see. And maybe that's the most extraordinary part of this whole story. Not the storms bigger than Earth, not the hidden oceans, not even the strange metallic hum drifting in from beyond the sun's reach, but the simple fact that a machine built with less computing power than a modern notification sound managed to outlast every prediction ever made about it, and is still, right now, quietly listening to something no human being has ever heard before, and still somehow finding a way to tell us about it. Think about what that actually means in practical terms. Every single day between now and whenever Voyager 1's last instrument finally goes silent, a team of engineers back on Earth is choosing to spend real time, real budget, and real attention on a spacecraft most people assumed had stopped mattering decades Ago. They're still parsing faint, garbled signals arriving nearly a full day late. Still deciding which watt goes where. Still writing and testing code for hardware that predates almost every piece of technology in your home right now. That's not nostalgia. It's active, ongoing science being extracted one careful decision at a time from the very edge of what a human-made object has ever reached. And it's happening in a decade when most of the public attention around space. Exploration is aimed at newer missions, fresh spacecraft heading to the moon and Mars, telescopes peering toward the earliest galaxies, private companies racing to build the next headline-grabbing rocket. Voyager 1 doesn't compete for that kind of attention anymore. And in a strange way, that's part of what makes it worth paying attention to. It isn't trying to impress anyone. It's simply still out there, still working, still sending back whatever fragments of interstellar space it can manage to capture before its power finally runs out for good. There's also something worth sitting with in the fact that nobody alive today will ever know exactly how the story ends. Voyager 1 will likely go silent sometime in the next decade or two. Its last transmission arriving on Earth long after most of the engineers who built it have passed away. But the spacecraft itself won't stop moving. It will keep drifting outward for millions of years after that final signal, long after every trace of the mission's original purpose has been forgotten, carrying that same golden record the entire way. A message in a bottle cast into an ocean so vast that finding it would take almost unimaginable luck. Nobody involved in launching Voyager 1 in 1977 could have guessed it would still be teaching us new things about the universe in 2026, let alone that a 50-year-old spacecraft running on a fraction of a modern phone's battery would still be humanity's only working set of eyes and ears sitting beyond the edge of the sun's influence. That, more than any single discovery along the way, might be the real story here.